So in lecture 10, we're going to talk about enzyme kinetics, and this is essentially observing reaction rates, how fast a reaction is going, when we change the conditions. If we change things like substrate concentration or pH or alter the enzyme, we can learn something about how the enzyme catalyzes its reaction. And so we can identify things such as what are the substrates and products for an enzyme. We can identify key amino acid residues that are involved in binding and catalysis. And we can understand things about the catalytic mechanism, even things like what's the transition state look like. And we can look at the order of substrate binding and product release. And so if you remember, we talked about ping pong mechanisms and sequential mechanisms and all those things. It's kinetics that enables us to make those determinations. And perhaps most relevant for us is that we can both identify and characterize inhibitors and drugs. Most drugs, most pharmaceuticals, have an enzyme target. And before a drug can go out in the market, there's a whole lot of testing that has to occur to ensure that it's safe and effective. But before we really get into enzyme kinetics, we definitely need to review chemical kinetics. And hopefully a lot of this is in fact reviewed for you. So if you remember some reaction, substrate being converted to product, or under the chemical kinetics terms, we would call that a reactant, but now we're going to use substrate anyhow. That the reaction coordinate for that is actually a little more complicated because, as we've seen before, there are intermediates and transition states. So while we're looking at delta G as a function of reaction progress, we can start off with substrates at some energy level. Most likely there are actually a couple different intermediates before we actually get to the product, and so we could potentially have one intermediate, two intermediates, who knows. But what really matters here, as we saw before, right, that it's the height of the energy barrier. It's the difference in energy between the substrate and the transition state, that delta G, or energy of activation. And that's what determines the kinetics. That's what determines the speed of the reaction. And this is governed by what we call the I-ring equation. You may have seen this in another form called the Arrhenius equation, where we have a lowercase k. So, if I got to draw it, I usually draw my lowercase k's with an exaggerated top part like that. Sometimes I'll draw them like that just to indicate that they're lowercase. Very different than an uppercase k, an equilibrium constant, or a Michaelis constant. These are lowercase. Equals some constant times e to the negative, all in parentheses here. We've got delta G of that transition state, so the activation energy, divided by RT, all within those brackets there. So this little a term is actually what we call the pre-exponential factor. It contains a lot of information about the particular reaction. So what's the likelihood that two molecules are going to collide into each other, that the nucleophile is going to be lined up with the electrophile, those sorts of things. So that's a part of K, of this constant that tells us about this reaction. But notice what's also important are things up in this exponential. So as temperature increases, so notice temperature is in the denominator, so a greater temperature is going to make this whole term here smaller, but it's a negative exponential, and so that's actually going to make that increase. So the reaction rate and K, it should make sense, increase as temperature increases, and we kind of know that. You heat up a reaction, it's going to go faster. But then notice we've got delta G, the activation energy, in the numerator. So as that increases, that makes this term larger, but it's a negative exponential, so it makes it smaller overall. And so this is reaction rate in K will decrease as the energy of activation increases, and that should make sense, as we've been seeing. That's going to indicate a higher energy barrier, and so K in the reaction will be slower as a result of that. So just a reminder about what lowercase k really means. So I want to talk about first order reactions and what that really means. And so when we say order, we're talking about really the number of concentration terms that appear in the rate law, if you remember that. So let's just say again, our reaction substrate going to product is governed by some rate constant K, just like above, that describes how that reaction proceeds. And the rate law then of this, the rate of the reaction, which is equal to, by definition, the change in product concentration over time. That's all dP/dt means in that case, is the change in the concentration product over time. That because of the law of conservation of mass, that's going to equal negative the change in substrate concentration over time. Those two are going to be equal and opposite. This is equal to some value K, as determined above, times the concentration of that substrate. And so we call that reaction velocity, and we'll give it a lowercase v. So to simplify all of this, we could say that that v for this equals K times S. So this really is the rate law for a first order reaction that has some rate constant K, again lowercase k, times that substrate concentration. So the half-life we talked about before is by definition the amount of time that it takes for a reaction to proceed halfway to completion, or rather the equilibrium, not that 100% of the substrate is going to go away. It's going to achieve equilibrium. And so we sort of use the symbol T1 half to indicate half-life. Now again, this is specifically a first order reaction. The half-life turns out, we're not going to worry too much about deriving all of this. They're integrated rate laws that you may have seen before, but we're not going to do that here. It's 0.693 divided by that value K, that rate constant K. So that is, for any first order reaction, the amount of time it takes for the reaction to proceed halfway to equilibrium. Notice that the concentration of substrate is not present in that. It's kind of interesting. Let's look at second order reactions, and these can take on a couple ideas. You could have perhaps one substrate and another substrate, so S1 and S2, that by some rate constant produce product. Or it could be two substrates that are identical to each other via some K that produce product. So as far as the rate law goes, these are second order reactions, so you're going to have two concentration terms. So you'll have velocity of the reaction equals K times S1 times S2 for the first example, and this other one, it's going to be velocity equals K times the substrate concentration squared, because there's only one type, just the regular one. It's only one of them. And so the half-life for this, if we go through and there's a derivation, which we're not going to do, T1 half for second order reaction is 1 over K times the substrate concentration at the beginning, S0. And so now for a second order reaction, notice the half-life is actually dependent on substrate. So the more substrate you have, the higher concentration you have of that, then the faster that reaction is going to proceed to equilibrium. And the smaller the half-life will be. So I want to look at rate constants and the units. This is very important, understanding how we're going to set up various things throughout kinetics. So let's look at, the way we have to do this is we have to look at the rate law. Must the rate constant be for that particular order? So for a first order reaction, right, the rate law is velocity equals K times S, remember from the previous. And let's just look at the units of each of those things to see determine what the unit of K should be. So the velocity should have units of concentration per time, right? We're changing concentration over time. So it's molar per second, like that. That has to equal K, and we'll leave this blank for now until we figure out what the units are supposed to be, times the the substrate concentration, and the units of that are going to be molar. Now they could be millimolar or something like that, but we're going to express everything in the base units here. So looking at this, how can we, on the left-hand side we have molar per second. How do we get molar per second on the right-hand side? We already have the molar, so we must have that, so K must equal inverse second, or per second in other words. So for a first order reaction, the rate constant K will have units of inverse seconds. And we use the exact same process to determine the units of the rate constant for a second order reaction. So velocity equals, now it's K, and let's do the simpler case where we've got the same substrate twice. And again, velocity still has to equal molar per second. That is the definition of velocity. Equals K, which we'll leave blank for a moment, times the substrate concentration squared, which will have units of molar squared. So now, again, molar per second on the left-hand side. We've got molar squared here. So how can we get molar per second? Well, we still need that inverse second, but we have to cancel out one of those molar terms. So the only way we can do that is if the units are per molar per second. And so for a second order rate constant, the units are inverse molar times inverse seconds.